So in this lecture, we will see about the something Compton effect and Compton scattering. Um, we will not derive the actual expression, just we see what is Compton effect with respect to the quantum mechanics. So what is quantum scattering? So quantum scattering or quantum effect is also called quantum scattering. This is discovered by Arthur Holly Compton. Is the scattering of the high frequency of photons after an interaction with a charged particle, usually an electron. If its result is decrease in the energy, increase in the wavelength of the photon, which may be an X-ray or the gamma ray photon, it is called Compton effect. The part of the energy of the photon is transferred to the recoiling electron. So this is the Compton effect, and this is the setup. This is the X-ray photons, and we have the inelastic collision with the electron. After the scattering, the scattered electrons move in the y direction with making an angle theta. We will see in the later. And this is the scattered photon. This is the scattered photon, and this is scattered electron. So uh, Compton discovered the scattering of high frequency photons. So this X-ray photon, or we see this high frequency photon with a charged particle, usually an electron. So with a charged particle, um, it result in decrease in the energy or increase in the wavelength of the photon, which may be an X-ray or gamma photon. It is called the Compton scattering or Compton effect. So Compton scattering formula, we will see the what is Compton scattering formula. So in 1923, Compton explained the X-ray shift by attributing the particle-like momentum to the light quanta. Einstein had proposed light quanta in 1905 in explaining the photoelectric effect, but Compton did not build an Einstein work. The energy of the light quanta depends only on the frequency of the light. Compton derived the mathematical relationship between the shift in the wavelength and the scattering angle theta of the X-ray by assuming that each scattered X-ray photon interacted with only one electron. This is the assumption made by the Compton. He will not use the mathematical relation of Einstein work. So he derived the following relation for the charge in wavelength. This is his equation: lambda dash minus lambda is equal to h divided by MEC 1 minus cos theta. So here the diagram is, this is incident photon, this is target electron which is at rest. After scattering, uh, recoil electron makes an angle phi. Here is the angle phi. Electron makes the angle phi with the x-axis. This is phi. And the scattered photon makes an angle theta with the x-axis. The initial This is the initial wavelength of the incident photon, and this is the wavelength of scattered photon. So if we write lambda f minus lambda I, that is lambda f minus lambda I, that is final minus initial, is equal to, it is delta lambda. This is equal to h divided by m naught c 1 minus cos theta. So in place of for electron, we will use lambda, wavelength of incident X-ray, and lambda dash is the wavelength of scattered X-ray, and me is the rest mass of the electron. Electron should be at the rest position. So this is Compton scattering formula, which is very useful to find the value of lambda or theta in the numerical problems. So why Compton effect is used? So Compton scattering is considered as important as it is the most probable association of high energy rays in giving being with the atomic nuclei. It is used in radiotherapy. It is also used in material physics to promote the wave function of electron in matter. And what is the difference between the photoelectric effect and Compton effect? So photoelectric effect happens in the bound electron. Photoelectric effect happens in the bound electron, while the Compton effect happens in the free or loosely bound electron. This is the basic difference between the photoelectric effect and Compton effect. In the photoelectric effect, a single electron absorbs the entire energy and the incident photon, but in the Compton effect, the incident photon only transfer a portion of its energy to one electron. So there is an absorption and there is a transfer of energy in the both the cases. Now next we will derive some de Broglie wavelength. In the last class we have derived some of the relations of lambda with respect to the its wavelength, its kinetic energy, and its Boltzmann constant. So we will see the first relation we have derived is lambda is equal to h by p. Second relation we have derived h lambda is equal to h divided by root over 2m in place, as we know that since p is equal to root over 2m e. Now the third relation in terms of electron volt, lambda is equal to h divided by root over 2m qp. This is the third relation. The fourth relation is in place of uh, energy, we have h divided by root over 2m kt, where k is Boltzmann constant. Boltzmann constant. Okay. Now we will use the relativistic condition. Relativistic condition. In the relativistic case, the kinetic energy have the relation E is equal to p square c square plus m naught square c to the power 4, where m naught is the rate mass of the particle. Also, we have the relation E is equal to T plus total energy is equal to kinetic energy plus m naught c square. And in the relativistic condition, we have T is equal to Q into V. So in place of T, we will substitute Q into V, m naught c square. Therefore, we have from this equation p square c square is equal to e square minus m naught c to the power 4, and in place of this we will write this equation, that is qc plus m naught c square whole square minus m naught square c to the power 4. After solving, that is q square v square plus 2 m naught c square qv plus m naught square c to the power 4 minus m naught square c to the power 4. Cancelling these two terms, we have q square v square plus 2 m naught c square qv. This is p square c square. So now we have to find the p square. So p square is equal to q square v square plus 2 m naught c square qv divided by c square. So Taking 2 m naught qv common, we have 1 plus qv divided by 2 m naught c square. This is p square. So we have p is equal to root over 2 m naught qv 1 plus qv divided by 2 m naught c square. So this is the value of p. Now we will use the special case. The special case, if the charged particle in an electron, if charged particle is an electron, then the charge q is equal to the electronic charge, that is 1.6 into 10 to the power minus 19 coulomb, and the rest mass of the electron is 9.1 into 10 to the power minus 31 kg. Putting all this value, here we will find that lambda is equal to de Broglie wavelength is equal to h by p. So this is h divided by whole this quantity here. So here lambda is equal to 6.62 into, after solving everything, 10 to the power minus 34, the value of h, this is the value of h, that is Planck's constant, divided by root over 2. In place of m naught we place 9.1 into 10 to the power minus 31. In place of q, small q, the charge of electron, 1.6 into 10 to the power minus 19 coulomb, and we will write 1 plus ev 2 m naught c square. Here also we have a v term, so we will write 12.1227 v to the power half 1 plus ev divided by 2 m naught c square to the power half. This is in terms of angstrom. We know that 1 angstrom is equal to 10 to the power minus 10 meter. This is the expression of for the electron in the relativistic case, and this is the general equation of the electron in the relativistic case. All the relations we have derived in the de Broglie hypothesis, that is in the previous lecture, that is lambda is equal to h by p, lambda is equal to h divided by 2 me. Whichever the cases, we will use these equations to find momentum, energy, charge or potential difference, temperature, or the, for relativistic case, to find the wavelength of that particles. So that's it, the basics of all the quantum mechanics. Now next we will start in the next lecture, that is the wave and its properties, wave mechanics, and the famous Schrodinger equation for time dependent, time independent, and for free particles.